All right, so welcome back, Fred. How you been?
I'm getting along.
All right, lots of schoolwork?
Yeah, lots of work, lots of craziness, trying to learn, trying to pass the classes, just trying to stay alive.
Yes, I get it. Okay, well, we're going to introduce to you a concept called percent composition. Percent composition. And this is kind of like something kind of familiar to you. You already know, maybe, that when we talk about, what percent of the cookies are chocolate chips, what percent is made of flour, right? That would be the percent composition, okay? We don't really use that sort of information very much in cooking. However, percent composition comes pretty handy when you're talking about what percent different elements are of a compound. So we go back to our Na2CO3. Do you remember the name of that compound now?
Let me look on my table. Oh yeah, sodium carbonate.
Very good, sodium carbonate. What percent of the sodium carbonate is sodium? What percent is carbon? And what percent is oxygen? And how do we get these numbers? Well, what we don't do is we don't say, well, there's 3 atoms of sodium and 1 atom of carbon, 3 atoms of oxygen. That's a total of, 2 atoms of sodium, 3 atoms of oxygen, 1 atom of carbon. That's a total of 6 atoms. So 2 of sodium, that's 2/6. We don't do it like that. We do it by mass. We determine percent composition always by mass, okay? So, if I look at the mass of 1 unit of sodium carbonate, now do you remember how to do this?
You have to get the periodic table out. Do you have the periodic table?
Oh, let me get that really quick. Okay, so here it is.
Now, you take 2 sodium masses. Sodium, where's sodium?
It's number 11 over here.
Okay, so it's 23 each. 2 times 23 plus the 12 plus, is oxygen 16?
Yeah, 16.
So 16 times 3 plus the 12 plus 2 23s, that would be the total mass.
That's right. So that's the mass for 1 unit. And then, let's see, if we do that in the calculator, that ends up being 106. Is that what you got?
Yeah, I got 106.
All right, good. So now we take the mass of just the sodium, which we said was 2 23s, right? We take the mass of 2 23s, that's 46, and we put that over the 106. And then that times 100, that's our fraction, multiplied by 100, and we get our percent, okay? So there is where we're going to get our 43.38%, okay? Good. So we took the mass, where did we get this 46 from?
That was the mass of the 2 sodiums, right?
That's right. This is our 2 NAs, and this was what?
That was the total mass.
That's right. That's the mass of Na2CO3. So percentage is, again, by mass of that given element within a given compound. Okay, very good. And the sum of the percentages are always going to add up to 100. All right. So, what's the percentage of carbon in carbon dioxide?
Well, let's see. Carbon's 12. I remember that. Oxygen 16. 16 plus 16, 32. Plus 12, that's 44. So carbon is the 12 of the 44. So 12 divided by 44 times 100.
Very good. Hopefully everybody at home followed that. But what you're saying basically is the mass of the carbon over the mass of a unit of carbon dioxide, right, times 100, and that will equal our percent, the mass percent of the carbon. Good. So I'm going to put the 12 over the 44, and I got 27.3%. Okay. Very good. Okay. Got it. We also can be given information about the mass of 2 different components in a compound. So maybe not necessarily the chemical formula, but just the mass of the two different components. And from that, we can add those together to get the mass of the whole. So if I want to know the percent nitrogen here, what would I do?
Well, you got the grams of nitrogen right there. They gave it to you.
Yep, I got grams of nitrogen, 0.1417 grams of nitrogen. So I just have to divide that by what?
The grams total, which would be, I guess, the grams of nitrogen plus the grams of oxygen.
That's right, 0.1417 plus the 0.4045. Okay, very good. And if we just multiply that by 100, that should be our percent nitrogen. Okay, excellent. And hopefully you got our 25.94. Now, what would we do to get the percent oxygen?
Well, I would just subtract it from 100.
That's right. Yeah, you could do that. Also, you could take the 0.4045 and put it over the total mass times 100 as well. But both of those should give you the same value. Good. Now, what about if we're given information like this? 35.5 grams sample and 23.5% of that is silicon. What mass of silicon is in the total sample? Any ideas on how you would approach this one, Fred?
Well, if it was 100% silicon, then it would be 35.5. If it was 50% silicon, it would be half that value.
Good. That's good thinking.
So what is it if it's 25%? If it was 25%, it would be 1/4 of that value.
That's right. How would you find out what half of 35.5 is?
I would take 35.5 and divide it by 2.
Okay, good. That would be half of 35.5. Could you also take 35.5? Is it the same as if you multiply it by 0.5?
Yeah. Multiplying by 2 is the same as dividing by a half, which is 0.5.
Okay, very good. Some old math tricks we learned there. So if it was half, this is if it's 50% silicon, right? Then you could get the mass of the silicon in the 35.5 gram sample by multiplying it by a half. And notice how that 0.5 is the fraction of 50%. Do you see that? You take the fraction, multiply it by 100, and that gives you your percentage, right? So we see that if you take this value, okay, so 50% of the 35.5 could be found by taking not 50%, but its fraction, which is 0.5, and multiplying it. And we can do the same thing to solve this sort of a problem here. Instead of taking 23.5, we take 0.235 and multiply it by our 35.5. And the result is going to be our grams that are silicon in our overall sample. Okay? So hopefully if you did that math, you got 8.34. Good. Now, we mentioned this already, that some molecules have a chemical formula that is not completely simplified. Our example was hydrogen peroxide. Remember how we said H2O2, and this is only for molecular compounds because ionic compounds, you always use the simplified, the most reduced form, right? But molecular compounds, you write the chemical formula that molecule actually does chemistry in, okay? We have a different name for the chemical formula of the molecule by itself, and also the most simplified form, and we call the most simplified chemical formula the empirical formula. The empirical formula, okay? The empirical formula for H2O2 would just be HO, all right? Glucose, our chemical formula for glucose, molecular formula is C6H12O6, but the empirical formula is CH2O. All right, you see that? You can also see that there's a relationship here, right? A multiplier exists between these two. If you take the empirical formula and multiply it by 6 in this case, then you get the molecular formula. All right? And this empirical formula information is useful because simply by knowing the mass percent, or the mass of the different components, the different elements in a compound, we can derive the empirical formula for that compound, okay? Okay. Here's how we do that. Here's how we derive the empirical formula from the information about the mass. Okay? We take our grams of material, because that's what the percentage information is, percentage information for the different compounds. We convert those grams to moles, all right? And after we convert them to moles, we can use that molar ratio to identify what the empirical formula is. So H2O2, the ratio of hydrogen, moles of hydrogen to moles of oxygen, 2 moles of hydrogen for every 2 moles of oxygen, right? Therefore, the empirical formula will have that same ratio. So as soon as we know moles of both of those, then we can use that information to calculate the empirical formula. So let's see if we can apply the information, what we've learned to this problem. 2.012 gram sample of something that contains nitrogen and oxygen, 0.522 grams of nitrogen, 1.490 grams of oxygen. And we need to calculate the empirical formula. Okay? So, what is the empirical formula again? Well, it's this N. We don't know these numbers now, so I'll put X and Y down there. But we need to know those numbers to get the empirical formula. And those numbers are mole ratios, the molar ratios, right? So, if I have grams of the material, I can convert those grams to moles. And after I get moles, then I can simplify that molar ratio and find out what the simplest molar ratio is. So, what did I say I wanted to get?
Moles. You need moles.
Yeah, so if I start off with wanting moles of nitrogen, for example, from the, how many grams of nitrogen?
0.522.
Grams of nitrogen. Then I can go from grams of nitrogen to moles of nitrogen. Do you remember how to do this?
That's just the number on the periodic table. Its units are grams per mole. So that nitrogen, I remember, is 14. 14 grams per mole.
Very good. So 0.522 divided by my 14, right? That's how I get, 0.522 divided by 14. That's how I get my moles of, there we go, moles of nitrogen, 0.0373. Okay? And for oxygen, what would I do?
Same thing, I guess, right? 1.490.
That's right, 1.490 grams of oxygen divided by my 16. 1.490 grams of oxygen. I'm going to go to moles of oxygen, and I need to get grams of oxygen there, moles of oxygen there, 16 for 1. Very good. 1.490 divided by 16. Okay, 0.093. 0.093. Okay. Now I have my information that I need, my moles of my different materials, nitrogen and oxygen, right? And I just need to use those values, N 0.0373 and O 0.093. Right? Now I can't stop there because that's not a whole number ratio, but one of the things I can do, a kind of little trick, is I can divide both of these values by the smallest number, 0.0373. That'll make this a whole number, 0.0373. Let's see what I get when I divide my 0.93 divided by 0.0373, my 0.093. I get 2.5. 2.5. Now, I'm getting closer to a whole number ratio, and I can kind of see that if I multiply this by 2, it'll make a whole number ratio. So if I do that, I have to multiply the other one by 2, and that gives me N2O5, whole numbers. This is molar ratio, right, because I converted the grams of each of these to moles, so I use moles. So that is the empirical formula then, okay?
Okay, I got it.